Let's talk about the Schottky effect. So we talked about having the barrier from the metal to the semiconductor as phi sub Pn. Well, turns out in a real Schottky diode it's a little bit lower, and that's due to this partially to the Schottky effect. Okay, so what is the Schottky effect? It is an image force that's on the electrons. And what do we mean by that? Well, let's consider this electron in a semiconductor. So this side is the semiconductor, and it's at a distance x from the surface of the semiconductor. Now I want to draw the electric field lines that emanate from this electron. So the way that I would do that is that I would draw in the metal a positive charge at the same distance. So this distance here is also x. And now if I have that positive charge there between the negative and positive charge, I can add the electric field lines. Okay, so there's the electric field lines between the electron in the semiconductor and this image force positive charge in the middle. That's actually not really there. We're just doing it so that we can draw these electric field lines, because the electric field lines don't actually exist in the metal. But if we do that, then we can write an image force that is on this electron in a semiconductor, and that's just Coulombic force. So it's going to be equal to this equation: F equals negative of the electron charge times the electric field. Then if we take the electric field and integrate it, we can get the potential energy of the electron. That looks like this. Okay, so here's the metal, here's the semiconductor. I'm plotting energy now on the y-axis. X-axis is still distance through the material. So the potential energy of the electron looks like this blue curve here. If we add up the effects of this potential energy of the electron and the electric field that's there due to this image force, this actually lowers the potential barrier at the metal semiconductor interface. Okay, so this dashed black line shows what the ideal case should be, and this blue curve shows what it actually is due to the Schottky effect, this lowering of that potential barrier because of that electron potential and the electric field. We can describe the lowering of the barrier by this equation, and we can describe the point at which the highest barrier occurs from the junction, that's x sub m, using this equation. But it turns out that if I calculate this delta phi, this doesn't actually tell me what this potential barrier is in a real Schottky junction. That's because we have all these states on the surface. Remember, this is an interface, so we can have states at that interface, and that also changes the potential profile here. So if you were to calculate what this delta phi is, and then you look at a real semiconductor, so pick a particular metal, say aluminum, and a particular semiconductor, say silicon, you can calculate what this barrier lowering is due to the Schottky effect, but because of the surface states, and we don't know what those are, it's not actually going to be the real value. Okay, so we're not really actually going to use this equation to figure that out. And instead, in order to figure out the value of that potential barrier, so phi sub Bn is the non-ideal value, we're going to look that up in figure 9.5 of your textbook, which shows the experimentally measured values of this potential barrier here.